first thing you're going to notice here is that this function is different from the one in your worksheet because the one on the worksheet is wrong. But it's the same thing. We're going to try and use Lagrange to try and figure out how close this is to this actual value. This is the fourth order Taylor polynomial for the natural log of 1 plus x with 0.5 of x plugged in. So we're going to need the fifth derivative and what's happening with x to the fifth all over 5 factorial. That's what's used to create the next term. The fifth derivative of this function takes us all the way down to this guy. And let's just talk about putting an upper bound on this. This is a little different from the previous ones we've had. So the idea is that we want to put an upper bound on the function that will be larger than any value between the center of the series, which of course is at 0, and the relevant x value, which in this case is 0.5. I need for this to be as big as possible. There's two ways to look at this. One way, is to recognize that this function decreases all the time for positive x's, and so that means that if we evaluate it at 0, it'll be 24. At 0.5, it'll be something less than 24. So I'm going to use 24 as my upper bound. The other way is to basically, like 99 times out of 100 with these types of problems, when you have that fifth derivative, you are checking the endpoint, which you know is like the biggest relevant x value you have, so 0.5, or you're checking the center. So you can just plug in 0, plug in 5, see which one is bigger. Either way, if I want to maximize this from all x's from the center to the relevant x values, I'm going to evaluate it at 0 and make 24 my upper bound. Now we have to figure out what's happening with this part, and this part's always the same thing over and over. You basically want to make sure that you have an x value that's as close to the center as you can get, but still hitting all your relevant x values. So for this one, you pretty much are always putting in like the largest x value that you need to worry about, which in this case is 0.5. So I want to use that. If I plug that in, do my calculations, that's my answer, and that means that this approximation will be within 0.0063 of the natural log of 1.5. I hope that's helping. It's helping. I know it is.